All right, so let's get started. We're going to continue with entanglement-assisted classical communication. What did we do last time? We drew a picture of the most general possible entanglement-assisted communication protocol over a quantum channel. That was all-encompassing, because that's the most general thing you could do. If you're not allowing any other resource. And then through a sequence of arguments, which amounted to using hypothesis testing and data processing and some other tricks, we established some upper bounds on a one-shot entanglement-assisted classical capacity. Okay. And then that was formulated in terms of hypothesis testing relative entropy. So from there, we have these theorems that connect hypothesis testing relative entropy to Renyi relative entropy. Okay? And then we got a bound on the asymptotic entanglement-assisted capacity. We're allowed to use the channel many times. And we proved that an upper bound is the quantum mutual information of the channel. Right? So that was like this. Very, very beautiful result discovered by Bennett et al. And today we're going to work on the lower bound. We're going to show it's equal to the mutual information also. Okay, and you'll see some interesting ideas. You know, there's really like a few, I would say, two key concepts for the lower bounds in devising a strategy. And so we'll try to go through that. So. Okay, so the one-shot entanglement-assisted capacity, it's a function of two things: an error parameter epsilon, that's a number between 0 and 1, and the channel itself. And intuitively, when you see this, it's like this is the largest number of bits you can send over the channel, and subject to the constraint that the error probability is no larger than epsilon. So that's what it is. And today we're going to establish a lower bound. And it's again going to be in terms of a mutual information quantity plus like a correction term. Okay? That's related to the error. Okay? And now we need to introduce this other parameter eta. And it's a different kind of mutual information. So we have to have a different notation. So we just decided to put a bar on top. This is the lower bound. So this holds for all epsilon between 0 and 1, and eta between 0 and epsilon. Okay. In order for this parameter here to make sense, it has to be between 0 and 1. So we need eta is less than epsilon for this to make sense. Okay. Now, so what do you see? This is a mutual information like quantity, and this is some correction term related to the error. And you know, it's the kind of thing when we go to asymptotics, this will just go away. And we'll be left with something like this. So what is this? We optimize a hypothesis testing mutual information over all possible input states. State omega is the output state. And this quantity delta. This is defined generally for a bipartite state with a different, it uses relative entropy, but without the optimization. That's the key difference. So that's the bound this time, right? And then if you remember, if we substitute this with quantum relative entropy, we get mutual information, okay? And last time for the upper bounds, we had a minimum over the second argument here, the second factor in the tensor product. The idea behind that was to get the tightest possible upper bound. Okay. Now we're trying to get a lower bound, and the technique that we use, the infimum is not needed. And anyway, the bound is tighter without the infimum, right? Because now we're doing a lower bound. All right, so that's the key idea. You know, the number of bits is larger than something that's like mutual information, like the quantum mutual information. So how we're going to show this, we have to come up with a coding scheme. We have to devise some kind of coding scheme, right? And a long time ago, at the beginning of the course, we talked about Shannon's theorem for communication and the idea of random coding, okay? So we're going to do something somewhat different from that. We're going to use an idea that people came up with around 2017. A guy named Nakib Warsi. So the background story is that he was reading my first book and found the proof of the coding theorem too complicated. He said, well, can we come up with a simpler idea? And then he came up with a beautiful idea. And so now I'm going to teach that. So it's called position-based coding, right? And the basic idea behind it is pretty simple. So to show this lower bound, use position-based coding. I'll explain what that is. And combines with something called sequential decoding. Right? And so these are really the two concepts that are there behind the coding theorem. There's going to be a fair amount of math to justify it, but I'll do my best to draw some pictures to give an idea of what these things mean. Okay, so in this information quantity, you're optimizing over bipartite states. Okay, and here I wrote psi. Whenever I write psi, that means pure state. Okay, so implicitly we're optimizing over pure states, and the reason why you can restrict to pure states is the same kind of thing we had before, where if you optimize over mixed states, well, you could purify anyway. From data processing, the information quantity would only get larger, blah, blah, blah. Okay? So, but the idea is going to be, this will be the resource state that will allow them to share. Okay? And whichever one optimizes this quantity, that will be a resource state. Okay? And for the most part, in general, this is going to be an entangled state. Okay? So that's how I want you to think about it. And then that's exactly what's going to, then the protocol will be about distinguishing the state that's generated by the channel. So that's this one, the state omega. So this quantity is a hypothesis testing quantity. And then when you see hypothesis testing, you're like, oh, it's about distinguishing this state from this state. Okay? And that's what the protocol is going to amount to. So there's going to be, eventually we're going to have a measurement where the problem is going to boil down to using that measurement to distinguish the joint state from a product state. Okay? So we're going to let rho A prime B prime be a resource state. Okay? And And in the entanglement-assisted setting, we make no restriction on the entanglement they can share. Okay? So we can give them a lot of entanglement. And this protocol uses a lot. Okay? We can return to that point later, argue that in practice, maybe it doesn't use so much, but the way we're first going to present it, it's going to be used in a lot. We're going to let Alice and Bob share m copies of this state. That state will be tensor M, where mod M is the number of messages they want to transmit. Big M is a message set, and mod M is the number of messages. Okay, so that's where it's a lot of entanglement. But let's just go with it. Okay. So to illustrate the protocol, let's talk about a simple case. Suppose that M equals 4. Okay. So the resource state that Alice and Bob share will be A1 prime, B1 prime, B2 prime, B2 prime. Now I'm labeling them, right? So this is one copy of row, second copy of row. B3 prime, B3 prime. Dot, B4 prime, B4 prime. Okay, so there's only 4 messages. And now suppose Alice wants to send message 3. Okay. What is the encoding scheme? It's kind of the simplest thing you can think of. Alice, remember, Alice has all the A's and Bob has all the B's. Okay. So Alice will just look at this system and send that through the channel. That's the encoding. So very simple, almost trivial, right? So the encoding is very simple. What about the decoding? Well, let's think about Bob, right? So what are the systems that Bob has? All these ones on the right, okay? So using these systems, it is now his task to figure out what message was transmitted, right? So what should we do? Let's think of something stupid first, okay? So suppose Bob looks exclusively at system B. It doesn't use any of the others. Is that going to be helpful? Well, I said it's stupid, so no, right? Why is it not helpful? Well, there's system B doesn't, like, suppose that Alice had sent this system through. Well, this is the same state. It's IID copies. And so the density operator here will be no different if Alice had sent this system to the channel or this one. So Bob needs to make use of the entanglement and the correlations. Okay. So the next idea is sequential decoding, right? So this is already the first part of position-based coding. You see that the code is based just on the position in this diagram of where the system is corresponding to the message that Alice wants to transmit. Okay. So sequential decoding, this is something where Bob can make use of the correlations. So what will he do? He'll just go by, look at the systems one by one. So he will examine B1 and B. Okay. And let's first do an exercise. So in the case that Alice sent message 3, what is the reduced state of systems B1 prime and B? So if you trace out everything but B1 prime and B, what are you left with? Somebody tell me. There.
Fixing up even
where these are the ones that are left. So Bob will examine these two. So what is the reduced state of those systems? I can't hear. Maximum mixed. Well, is this a maximum mixed state? It's just the general state. Right? So, tensor product. Good. That's the key idea. It's a tensor product state. So this state was rho A1 prime, B1 prime. So the reduced state here is rho B1 prime, right? Where that's the reduction of this. And then the reduced state here is, we're tracing out this, tracing out this, tracing out this. So what's left is we're sending rho A3 prime through the channel a little bit, and right? But this is the same as rho B prime tensor. And the system A prime is isomorphic to the channel input system A, right? So let's make that clear. We're going to be using that for that. Okay, so it's a product state. And then what do you see? Well, this is precisely the state that appears as the second argument of this mutual information. Right. Except now the system R is like the B prime system. Okay, because now we're thinking of that as being in the physical protocol as being with both. Okay. All right. So let's do the same. Let's continue this exercise. So the reduced state of B2 prime and B. Same thing, yeah, product state, right? So B2 prime and B is a product state. Same thing as here. Yep. So because things were chosen to be IIT here, then the reduced states are always the same. Okay, let's first do the reduced state of B4 prime and B. Right? That's going to be the same thing. So B4 is uncorrelated. See, in the beginning, B4 prime was uncorrelated with A3 prime, and then the channel doesn't create correlations, right? It just acts on A3. So again, you have the same thing. Rho B4 prime. B. Now, okay. And now the key difference is here. The reduced state of B and B3 prime. So what is that? General state, yeah, like in general, like the channel acting on A prime of this state. Good. So this should give you an idea for a protocol, right? For Bob's, for a decoding scheme, for a measurement scheme. What is the idea? Suppose that from the hypothesis testing relative entropy, we know there's a measurement that can distinguish up to some delta for the type 1 error probability. It can distinguish the first argument from the second argument, right? The state in the first argument from the state in the second argument. So, and that's a binary measurement. It tells you, yes, it's the joint state, or no, it's the product state. Right? So sequential decoding just consists of doing these sequential tests, binary questions. You know, we said that measurements can be thought of as questions that you're asking to a quantum system. Right? So in this case, what are the questions? So Bob's decoder will just be on V1 prime and V. Is it the joint? Is it the correlated state, or is it the product state? Because he doesn't know. He doesn't know which choice Alice made. He's trying to figure that out. Right? We know because we have the whole diagram, but he doesn't know. So he does that measurement, and in this case, the truth is that no, it's the product state, right? And so that's what we want the answer to be. That it gets the measurement. But there's certain probability, right? So it doesn't happen with certainty. So what we want with as high as probability as possible, the answer to be no, it's a product state. But then when it goes to here, the reduced state is a product state. So we want it to be, when it does this binary measurement, no, it's the product state, right? And then in this case, it's meshes through ascent, and this is a correlated state or joint state. We want when it does this measure, the same measurement here, the outcome is yes, it's the joint state. And so that's sequential decoding. You want the answers to be no, 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 until you get a bingo, yes. You know, that's the message that was sent. That's the idea. Yeah.
There would be a short case.
This is one shot. The channel is usually one time.
But then it's eventually going to destroy state.
Excellent observation. So we have to overcome that, and we will. So is it clear what the observation is? You know, in quantum mechanics, when you do a measurement, you disturb the state, right? So this system D is being reused. Here it gets used once, twice, 3, 4. And so there's a risk that when you do this measurement, then you'll disturb the state, okay? We never talked about it actually, and that was unfortunate, but there's a principle called gentle measurement in quantum information. So the principle is this. I just want to talk about, this is like a little segue. Gentle measurement. This is something Andreas Winter came up with. In his thesis, he called it tender measurement, which is kind of funny sounding. So the statement is this. Suppose that a measurement operator, when acting on a state rho, has a high probability of success. Then what you can show is that the post-measurement state is not changed very much. Okay? So it's a particular post-measurement state where you sandwich by square root of lambda. I think you just okay. So that's a basic principle that we have. We're going to use a generalization of this called the quantum union bound. Okay? And that's how we'll make sequential decoding work. This quantum union bound has a little bit of history. Bernard Sen proved the first version of it in like 2010. We were together at McGill when I was doing my postdoc, and he was there visiting. And then I generalized that to POVMs using name marks extension theorem. It was kind of simple. And then a researcher from China, his last name was Gao, he improved it. And then some co-authors of mine and myself had the final word, the final improvement on the quantum union bound. And so that's what I'll show you today. All right, good. So that's the plan. And Yeah, indeed, the main obstacle to overcome is the measurement descending state. Okay. All right, so let's discuss the proof. And for that, I think we'll just erase the left one. Okay. So we're gonna let lambda b prime b. So that's going to be a measurement operator that can act in the b prime system and the channel output system b. Okay? So we're going to let that be an optimal measurement operator for the hypothesis testing relative entropy. I'm just going to abbreviate that as HTRE, hypothesis testing relative entropy. Okay? And it's going to be this one. Right here. Okay. And I think it's good to remind you of the definition. We've used it a number of times, but let's just remind ourselves of the definition. So the minimal type 2 error subject to a constraint on the type 1 error. I'll just, this goes here. Right? Such that and the BB prime measurement operator. And the type 1 error is no larger than epsilon minus eta. We put this eta to have a little wiggle room. Turns out you need it for technical reasons. It's unfortunate that you need it. Well, I guess it's really not that bad. Just makes the notation more pointy. All right, so that's the definition. And the basic idea you should have is that this is a measurement, because it's optimal, that somehow distinguishes this state from this state well. Okay, and it'll distinguish it well enough that we'll be able to get the bound stated in the theorem at the beginning. Okay, so we're going to need to implement this measurement, and we need an idea from earlier in the course how to implement measurements, name-marked extension. Okay, so lambda b prime. So this measurement implemented using the name-marked extension. So that's nice. We get to use a concept from earlier in the course. Okay. How will we do it? We'll use a projector. I. And we'll need an auxiliary system R. Okay. That'll be, remember, it's the name-marked extension theorem involved. There's the state you want to, there's the system you want to measure, and then you attach an auxiliary system prepared in a pure state to a unitary and then a von Neumann measurement on the probe. Okay. That's how we're going to do it. All right, so what is this? Okay, what will the unitary be? We'll make this choice. Okay, identity on R plus this you can write compactly as sigma x, sigma z. Let me just briefly remind myself of that term. So, yeah, 1, 0. This is the same as 1, 0 minus 0. But the key thing is that it has the name arc extension property. So if the state you're measuring is the joint state, right, like that corresponds to this state. And you attach the 0 state for R. And you do this, you get this outcome I. Then this probability of getting this, the probability of getting this outcome is equal to this one. That's all we're doing. And then that we know is guaranteed to be larger than 1 minus a small number. Okay. All right. And then the other thing we know is that when we take negative log, there's 2 trace, the same measurement operator acting on the product state. We said at the beginning, this is an optimal choice for this quantity. This quantity you can abbreviate. We use the notation at the beginning. Sorry, we have a lot of notation. You can abbreviate this like this. Where the state C, V prime D is the channel acting on the resource. Okay. So this quantity right here is equal to this. All right. So now we have to do the analysis of sequential decoding. Okay. So we just have to analyze the error probability using the scheme, and then that's basically it. Okay. And the key tool we'll need is this quantum union bound. All right, so I think I have to erase this stuff. Maybe I'll try to keep this part. All right. So let's define PI to be the measurement operator pi acting on I V prime system, channel output, and a auxiliary system. Okay, so for every V1 system, there will be an auxiliary system. That's going to help to do the measurements. For each one. We're going to do these sequential tests. And for each sequential test, because we'll need projection measurements to invoke the quantum union bounds, we'll need these auxiliary registers. Okay, so we've now introduced them. All right. So we'll define that like that. So, for example, P1 would be the measurement on V1 prime R1 channel output B. P2 would be V2 prime R2 B. Okay. So this is, you should think of this outcome as saying like, yes, that's the message. And then we'll define the complement. We'll put a hat on top. That will be no, not the message. And I should be clear, we should be clear that this operator actually has implicit identity. This is acting on, if I is 1, it's acting on V1 prime, R1, and B. Right? It's implicitly tensor with identity on these. It's not acting. Okay, we're not going to write all those tensor products. All right, so what is an algorithm? Sequential decoding algorithm is simple. I and just looking over all the messages. Measure should probably index proper pseudocode. Measure PI complement. That's a binary outcome P of M. Until outcome PI is entangled. That's the algorithm. Right? Simple enough. And then, like, if you never observed the first outcome, well, you made a match. Okay. So, what is our next task? We have to figure out the probability of making an error. Okay. So suppose that message M was is the one that was sent. Okay. Suppose that message M was sent. In this case, it's message 3. So what is the probability of correctly decoding? Well, we should get no, no, yeah. So we'll write that as probability of successful decoding message M. So what you can work out using the Born rule, like kind of recursively, is let's say that the state, the overall state with all these auxiliary systems as well is a state omega M. Okay, so that'll be the state of Bob's systems, of the state right here of Bob's reduced system. Okay, I'm going to suppress the system labels, but it's going to be V1 prime to V big M prime, R1 to R big M. Those are the systems you want to see. We'll write it in a second. So then we said we want to obtain the outcome no. right? So the message 3 was sent, we want to get no, no, yes, right? So put that there. Let me just write it and then I'll explain it. So this is not so obvious just from the Born rule itself, but if you apply it recursively, this is what you get. So this right here is the probability of getting a bunch of m-1 no's in a row when you check for messages 1 through m-1, and getting the outcome yes for message n. So this is the probability of correctly decoding. Why is that? Well, you can think about it. You can apply it recursively, and then you arrive at this conclusion. So when you do the first measurement, there's a probability to get the outcome no, and there's a post-measurement state. That post-measurement state is the normalized version of this. So then that's how this addresses your point, right? That's the state, the new state that gets disturbed by this projection. But then that's the new state that you check when you do the next measurement, right? And then if you normalize and apply things properly, you arrive at this conclusion. And so embedded is each of the post-measurement states in this expression. All right. Any questions about that? Okay. So the error probability is 1 minus. Okay. So the next part, I'm just kind of actually, I think I should give a proper background on. So what is the union bound and how do we use it? It applies to events. Call them A1 through A9. And the quantum version of these events are projections. Okay. So when do you apply the union bounds? Well, an analogy to what we're thinking about here, we want a certain sequence of events to happen. Right? So in classical probability theory, that's an intersection of events. Right? We want to no, 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 and yes. So that's all those events occurring. They have an intersection, and that's the correct sequence of events. So A1 through A N, right? But then we're interested in bounding the error probability. So the error, this is the success, this is the probability that a correct sequence of events happens. That's a success probability. And error probability is the complement. Okay? And then you apply the Morgan's law. And with A1 complement union, the intersections flip to unions. Right? And what does the union bound say? Well, it says that the probability that at least one of these events happens, that's the union of the events, is bounded from above by the sum of the probabilities of the individual events. That's what it says. Okay, so we want a quantum generalization of this. All right? So the quantum union bounds, what does it say? And it has its own proof. But ultimately, the proof, like, we just ended up using Pythagoras' theorem and Cauchy-Schwarz. So, like, the basic math behind it was simple, but arriving at it was took a long time. Okay. So what does it say? let's just write it for this case, right? Why don't we just apply it directly rather than writing it here? So these projectors multiply each other. That's the quantum. That's like a quantum generalization of intersection, right? If these projectors are commuting, that reduces to the classical case. They're commuting, and then you can directly apply the classical union theorem, right? But in general, for the quantum case, these projectors are non-commuting, right? And especially the case that we're analyzing with entanglement and quantum channels, you know, these states and these tests are non-commuting. Why? They're all overlapping on the V system. Okay. So you know, the classical union doesn't apply if the projectors are non-commuting. Right. So we said that this multiplication of projectors is like an intersection. Right? Let me illustrate why that's the case by an example. In case it's not clear. Here's a projection, right? Here's another projection. So let's call this P1 and P2. These are commuting, right? So you know, this will give an outcome. This will give a click of a photon detector if you have no photon or one photon there, right? This one will give a click if you have no photon or two photons, right? The intersection of those events is zero photon, right? When we multiply these two projectors, what do we get? The projection onto zero. So that's how that's how you can think of the classical case. How intersection of events is like multiplication of commuting projectors. Right? There's a whole field of study called quantum logic, which is very interesting from a mathematical perspective. Okay, and von Neumann, of course, contributed to that. He did like everything. So, unfortunately, he left. So, okay, what does the quantum union bound say? The classical one said you take the individual events that are there in the correct sequence of events and you sum the complement. Okay? So, what is the complement of this one? You put a hat to get identity minus that project, right? So the quantum union bound, there's going to be a factor here. I'll fill it in later. So we'll have the complement of this one. Plus another prefactor. Fill it in a second. And the sum. And now these are all, they have hats on top. So their complements are each without the hat. Sum I went from 1 to m minus 1 trace p I m. Okay. So if these prefactors were 1, this would be precisely the classical union thing. Okay. So what is the best thing that we can do? And I think there was even a follow-up paper called Quantum Union Bound Made Easy, put out by some researchers at Carnegie Mellon, computer scientists. And they proved that there was a sense in which the bound we'd come up with is essentially optimal for the quantum. So we need prefactors. 1 plus C, 2 plus C plus C inverse. But this holds for all C strictly greater than 2. Okay. So what's going on is that in the classical union bounds, all these prefactors can just be 1. In the quantum one, you can tune this parameter C to become arbitrarily close to 0 at the price of a blow up in this term. Okay. And you know, it seems that this kind of thing is necessary. You could also pick C to be 1. and you'll get 2 here and 4, and then you just have a prefactor of 4 in front of all the terms. And that's what Gao did, the Chinese researcher, in that was like 2014, 2015, something like that. Okay. So that's the story of the quantum union bound. All right. I need to make some room, so I'll eliminate this last thing. But we didn't yet define the state omega m. Let me write it properly. So omega m is a state on systems B1 primes or Bm prime R1 through B R1 through R m. And it's given by just the reduced state of Bob's systems sensitive with the 0 state. So it's right there. Rho B1 prime product, tensor product with rho -1 prime tensor. And then the bingo state is the messages here, the correlated state. M's. One, and then tensor, you got to fill this algorithm. And then just a bunch of zeros. R1 through R big M. So that's right. So, R1 through R big M. Okay. How can we rewrite this probability? So this is where there's a match between, sorry. This is where the message that's sent matches the measurements. The indices match. That's all I'm trying to say. Right? And so this will be identity minus pi acting on omega m. How will that collapse? So we have information here that we can use. It's one or the other, right? There's only 2 choices for how it will collapse. It's going to collapse to either this or to this trace expression. So which one will it be? Modulo like identity minus it, right? So which one will this collapse to? First one. This one. Yes. An identity minus line. Yeah. Why is that? That's when this corresponds to, this omega m is this whole state. And then this measurement operator is when Bob is actually doing the test on these 3. The correlated state is there, and then it's here. Right? And so this was pi, right? This PM hat corresponds to identity minus pi acting on this state, and then we said from Neymar it collapses to this. Okay, fine. There was a point I forgot to state with the quantum union bound. It only applies to projection. That's why we have to do this whole thing where we use Neymar extension. But I mean, like, yeah, it's not so bad to do that. All right, so this will collapse to 1 plus c trace identity v prime b minus lambda v prime b. Acting on what about the other one? So first of all, there are m minus 1 different terms. Are they all different or are they all the same? They're all the same. Good. Right? It has to do with the symmetry of the protocol, right? Like we chose an IID state. And then at the beginning we said, whichever one is not correlated, it's all the same state. And then the probe or test that you're doing is always the same binary measurement. So these all collapse to the same expression very nicely. So there's m minus 1 of them. And it's going to be this. There's a typo. I forgot to put tensor was 0. But anyway, that collapses to trace lambda v prime b rho v prime tensor n. Right. This itself we can rewrite as using this hypothesis testing relative entropy. Allow me to introduce an abbreviation, otherwise, there's already a lot of notation at the board, right? And let's just call this IH, right? So that we don't have to write bar epsilon minus eta, b times, blah, 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 right? So let's call it IH. So this IH has a negative log in front. So then this term here we can write as 2 to the minus IH. Substitution. Why can we do that? We chose lambda to be the optimal measurement output. Okay, so we can make that substitution, and we can apply this constraint. Right, this lambda satisfies this constraint. So identity minus lambda here will be less than epsilon minus eta. So let's do that in upper bound. 1 plus c epsilon minus eta. We're now getting very close. Very close. 2 plus c inverse. Little m minus 1, that's going to be less than the total number of messages. So it's just bounded from above by the total number of messages. And then 2 to the minus I each. That's a nice balance, right? Why is it nice? Well, now all it depends on are some parameters, some key parameters of interest for communication. Number of messages, information quantity, it's just a function of the channel, and then this error time. Okay. So now we have to do a little trick. The other point to make is that what's also very nice about this bound is it's a uniform bound, independent of the choice of message. So this is a uniform bound. This is going to be a bound of the maximal error probability, because it's a bound of the error probability for all possible messages. Right? So uniform bound. Maybe we'll put an exclamation here. So if we pick C equal to beta over 2 epsilon minus eta, and if we pick M to be 2 to the IH, we're using this abbreviation, right? 2 to the IH. And then in the exponent, that thing we had in the beginning, minus log 4 epsilon over eta squared is going to be particular. But if you make these choices, and you do algebra, i.e. plug in Mathematica, then you can bound this error probability from above by epsilon. So, yeah.
So the message, does it have to be?
Does it what?
Does the message?
Integer? Yes. Oh, okay. Good point. Yes. We always ignore that. Do like floor. Yeah. 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 It's yeah. Just, so that's the end of the proof, right? That proves the claim at the beginning. Why is that? We did everything we were supposed to do. We showed an example of a communication scheme such that for all possible messages, the error probability is less than epsilon. That's the target, right? Because we wanted to get the bounds. We were interested in the epsilon one-shot capacity, right? So that's the key parameter. And then by doing all this fine tuning with parameters, we showed that for this position-based coding in conjunction with sequential decoding, through the analysis of the quantum unit bounds, you get an upper bound on the error probability is epsilon for all possible messages. As long as we choose the number of messages to be this amount, to be that size. Okay? And then modulo the point Roy identified that indeed the message should be an integer. We have this lower thing. Okay. So there's a final point to make. At the beginning, we let the we assumed that the entangled resource state was just some state really good, right? But now we can show we can optimize this information quantity with respect to all possible input states, and then by optimizing by h over input states, we get the claimed bound at the beginning. And that we wrote, that equals greater than. Okay, that's the whole thing. So pretty different from Shannon's idea, right? We didn't make use of typical subspaces, typical sets, or we didn't even make use of random coding, right? But we used a hell of a lot of entanglement, right? And so how can we argue about the entanglement usage to sort of not to argue that it's not using so much? Well, if we imagine there's like a bank of entanglement available to which we can consume and add, right? And suppose this is like a bank of entanglement, right? In this protocol, we use just one state. Right? And when that's gone, these are still available. Then we could bring in one new state in the next round. However, we did disturb the entanglement. We did measurements. We did measurements here, so we disturbed it a little bit. But this gentle measurement lemma, if the measurement's successful, we disturbed it only a little amount. Okay, so that's the basic idea behind why. In practice, maybe it's not using so much if you have this entanglement reserve, which we hope would one day be available. All right. Good. Any questions about any of this? We'll now go on to asymptotics. Yeah. This state omega?
Yes, so the row.
Yes. This is the state of Bob's reduced systems. These ones here.
So
When message, oh yeah, sorry. This one, this one, this one, this one. That's Bob's reduced state if message M is transmitted. Okay.
so after the one chain, what do you think some of those things?
What's this right here? So these are the reduced states. So there's the entangled resource state. Right? And in this picture, this is not available to Bob. This is not available to Bob. This is not available. So it gets traced over. So in this picture, omega M is the state of these systems, the rightmost systems. Right? And then this is the marginal of this state. This A1 is not available. So that's this right here. Right? And then it's in tensor product with everything else. That's that. And then M-1 is just 2 in this case. That's also a marginal state. This A2 prime is not available. Right? It's in tensor product with everything else. And then this is the one where the message is code. It's these two right here, right? And then same for these other ones. It's just B4. Right? And then these zeros are these auxiliary systems brought in to help out with the measurement.
So that's a little bit.
This right here is a lowercase m. Yeah. These are big M's. This is the only big M. Everything else is smaller. Yeah. Yeah. Once. Yeah, but we use quantum union. We actually, I just had like a sidebar discussion about gentle measurement. We never used that. Oh, yeah, the overall measurement is successful with, this was an error probability, so the success probability is greater than 1 minus epsilon. So we didn't make that part so precise, but just kind of intuitively, under the scheme, this whole measurement together is successful with probability 1 minus epsilon. And so the post-measurement state will not change very much. if epsilon is small. We always think of epsilon as small. Yeah. And there's a way to make this precise. We didn't get into the book because we didn't need it. Does that address the question? Yeah.
The extra policy should be good. Is it possible to do it?
The blocks.
So if the message is not visible now, the second set, it's not in the first set, and then it's negative.
Like a binary search.
Yeah.
That's very interesting. Yeah. Think about it and present it for your final project. I believe that I don't know that this has been precisely addressed with position-based learning, but I do remember reading some paper of Vittorio Achievability, a student of his, where they looked at this kind of binary search for Decoding. Yeah. And then, there's other schemes, at least for unassisted classical communication, use polar codes, and it does, in some sense, become like a binary search. We talk about it. So that's a nice insight. It's a very good point because in this class we're not concerned about computational runtime, right? How long is this going to take? Linear and big M, right? I mean, like big M number of messages, so that many like quantum computations, right? But guess what? Big M, when we go to asymptotics, that's going to be exponential in the number of channel uses. That's very bad, right? And so binary search is like the perfect thing you would do to reduce the complexity. Log of that, then linear the number of channels. Yeah. Good. All right. 3 minutes to talk about asymptotics. Maybe we can do it. We're just going to do kind of the similar thing we've done before. With this bound. Asymptotic. All right, so how is it defined? Same thing we did before. Use the channel little n times. So now this is bits. Divide by n to get per channel use. Take the limit as n goes to infinity. Epsilon goes to 0. That's the asymptotic capacity. All right, we want to get a lower bound of this. So remember this bound. Hypothesis testing relative entropy can be down from below by Petz-Renyi relative entropy. This holds for all alpha epsilon to 0. Okay, if we use this lower bound is a hypothesis testing relative entropy. Okay, so use this. Yeah, it's lower. C. This hypothesis testing mutual information will be converted to a Petz-Renyi mutual information. Bar. Bar means you're not optimizing over the second argument in the relative entropy. This correction term. Here we need epsilon minus eta. And then plus this other thing. Okay, so, and this holds for all alpha epsilon between 0 and 1. eta between 0 and epsilon. Okay. So now plug in the tensor power channel. Pi by n. Get this. All right. This quantity is super additive, right? I'm not arguing that it's additive, but I'm arguing it's super additive. That means you can do this. Why is that? This involves an optimization over all possible input states. It can involve entangled states across all the channels. You could pick in the optimization a tensor powered state. Right? And then using the fact that the Renyi relative entropy is additive, you get this. Right? So we'll just leave it at that. Then you get, plus this other stuff. Now we just take limits. Right? So it's similar to the kind of thing we did previously. Take a limit. This thing gets large. And all this stuff over here goes away. Right? We're left with that. This holds for all alpha between 0 and 1. Because it holds for all alpha between 0 and 1, you can take the limit. You can take a maximum over alpha between 0 and 1. And that's the same as, in this case, it's the same as taking the limit as alpha goes to 1. This is now the mutual information of the channel. Okay? This is equal to that's the mutual information of the channel, and then that's pretty much it. And then this, all this development holds for epsilon between 0 and 1. Now you can take the gamma over epsilon. So all this order of limits matters. So okay, and then this, is the asymptotic statement for this lecture, right? Coupled with the upper bound from last time. And then we get one of the most beautiful theorems in quantum information. Right, so just to summarize what it's saying, over on the left, we have an operational or physical quantity, the maximum number of bits, the maximum rate at which you can send classical information over a quantum channel if you have entanglement assistance of any kind. Okay? And it's saying that that physical or operational quantity is equal to this simple function, a simple mathematical function, formulated in terms of mutual information, which is like a correlation measure between the input and the output of the channel, a quantum correlation measure, because it's quantum mutual information. It's known that This optimization problem is concave to the input. Okay. And since you're maximizing a concrete function, which looks like that, roughly, right? Okay, the top. The point is that there are algorithms also that are efficient in the dimension of the channel for computing this speech information. And so it's like a nice, complete solution for this problem. And then everything else from here is a total mess, which is good for research. So, all right, let's stop there. See you Monday.